Welcome everyone. So, in the last lecture we discussed about radioactive decay scheme. We saw that if there is any radioactive isotope, for instance if you are talking of carbon 14, let us say, which we know it decays to nitrogen with a beta decay, right. So, what happens is, if a parent nuclide decays to a stable daughter, this is a parent which is a radioactive and this is a daughter product which is, let us say, stable, because we know carbon nitrogen 14 is stable. In that case, at any given point of time, the number of atoms that is there for carbon 14 for time t will be equal to n0 e to the power minus lambda t. So, they will follow an exponential equation. So, they will start with n0, let us say t is equal to 0, the total number of atoms of carbon 14 that was there is n0. Over period of time they will decay. So, the number of carbon 14 atoms will decrease and that decrease will follow an exponential pattern. This is what we discuss today. Now, what we will discuss today is, if this daughter is not stable, if the daughter itself is radioactive, how this equation will follow. So, there are several examples where the daughter itself is radioactive. To give you an example, let us say you have uranium 234, if that decays to thorium, of course, you can see that there is a alpha decay. So, there has to be 2He4, it is a helium atom. So, 92 became 90, to 34 became, this has to be 230. So, if the half life is about 250 kilo years and the 230 thorium, which is a daughter, itself is radioactive. So, it will decay further in a lifespan of in a half life of 75 kilo year, and it will produce radium 226. Well, if you continue like this, even radium itself is radioactive, it has a half life of 1600 years, it will give you radon 222 and it keeps on going. But what we will focus is this part, apparent, well, 234 uranium itself is radioactive, we will not worry at that moment. What we will target today is only this much. So, what happens if a daughter itself is radioactive, then how do this equation looks like? Let us say this is N1, this is N2, the number of atoms we will represent them N1, N2, N3 and their corresponding decay constants are lambda 1 and lambda 2. So, what we are targeting, that there was a parent N1 which has a decay constant of lambda 1 which produces a daughter N2 which itself is radioactive and has a decay constant of lambda 2. We need to find out the rate of change of N2 over period of time, and that rate of change of N2 at any point of time will depend on two things. One is production of N2 through decay of N1. So, there will be a radioactive production which we call as a radiogenic production of N2 via N1, and there will be another component where N2 itself is radioactive. So, its loss due to radioactivity. So, this rate of change of N2 will be equal to 1 is a decay term which should be lambda 2 N2 and there is a supply from decay of n1, which should be lambda 1 n1, which means if you simplify this, dn2 by d2 dn2 by dt plus lambda 2 n2 will be equal to lambda 1 n1. So, the minus minus cancels out, you have n1. We know n1 is actually equal to n1 0 e to the power lambda 1 t. So, this is same equation, n is equal to n 0 e to the power minus lambda t, because we are talking of parent which has a decay constant of lambda 1, and if the starting point is n1 0, then if you replace this, this is dn2 dt plus lambda 2 n2, that will be equal to lambda 1 e to the power minus lambda t. So, this is our equation 1, and this is called as Bateman equation. So, Bateman equation actually reflects the rate of change of N2 based on its own decay and the production through the decay of N1 in a decay constant lambda. So, we will try to solve this out and see what comes out. So, let us say we will multiply equation 1 with e to the power lambda t. So, either side I will multiply with e to the power lambda 2 t, then what will happen, this will be like, first we will change this as dn2. So, I am also multiplying with dt, so that everything becomes in one form, e to the power lambda 2 t plus e to the power lambda 2 t lambda 2 n2 dt, that will be equal to lambda 1 n1 0 e to the power lambda 2 minus lambda 1 t. So, basically I have taken out this dt. So, this here there is a dt, here there has to be a dt, and also I multiply the equation 1 with e to the power lambda 2 t, which is there in everywhere. So, if you try to integrate this, so this will come as d of if you look it carefully. So, this is a derivative of n2 e to the power lambda 2 t as it is, and n2 is as it is, and if you differentiate this e to the power lambda 2 t and lambda 2. So, this is basically a differentiation of n2 e to the power lambda 2 t, that is what is written here, integration lambda 1 n1 0 e to the power lambda 2 minus 1 t dt. If we put some limits, the 0, this is also 0, if this is t, this will be 0 t. Alright, so this term comes out. So, this is n2 e to the power lambda 2 t 0 to t, and this will be lambda 1 divided by lambda 2 minus 1, n1 0 of course is a constant, e to the power lambda 2 minus lambda 1 into t between 0 to t. So, if I write this again, first if it is n2 e to the power lambda 2 t minus n2 0 e to the power, so e to the power lambda 2 t becomes 1. So, we can write n2 here, that will be equals to lambda 1 lambda 2 minus lambda 1 n1 0 e to the power lambda 2 minus lambda 1 into t minus lambda 1 by lambda 2 minus lambda 1 n1 0. Now, if we multiply with e to the power lambda 2 t, so we will multiply this equation with e to the power lambda 2 t. So, multiplying with e to the power minus lambda 2 t, then e to the power lambda 2 goes out. So, n 2 minus n 2 0 e to the power minus lambda 2 t will be equal to lambda 1 by lambda 2 minus lambda 1 n 1 0 e to the power minus lambda 2 t. If we are multiplying, then this becomes e to the power minus lambda 1 t, and the second term is actually common. So, we can write this as e to the power minus lambda 2 t, right. So, this n 2 at any point of time basically is lambda 1 lambda 2 minus n 1 0 e to the power minus lambda 1 t e to the power minus lambda 2 t plus this term I am taking to the right hand side. So, this becomes n 2 0 e to the power minus lambda 2 t. So, this is the expression that represents the number of radioactive daughter n 2 at any point of time. You will see in the right hand side you have two terms. One is n 2 0 e to the power minus lambda 2 t. So, this is exactly same as something very similar to n is equal to n 0 e to the power minus lambda t, right. So, this term basically reflects the decay of n 2 with a decay constant of lambda 2. So, this is exactly the decay equation for an element n 2 with a decay constant of lambda 2, if that is there. So, this term reflects this, and this term basically physically signifies that decay of n 1 that has produced n 2, but till this point it is not yet decayed further to produce n 3. So, there has been a production of lambda 2, and out of that production there will be something that goes to n 3, but that has not still happened. So, this is the amount of n 2 that is still alive. So, this is the term that which reflects this, all right. Now, generally to start with, whenever you have a system, this n 2 0 is 0. So, often you will see that n 2 0 is found 0. In that case, this equation simplifies further and n 2 became lambda 1 lambda 2 minus lambda 1 n 1 0 e to the power minus lambda 1 t minus e to the power lambda 2 t. So, this is the equation if you do not have any n 2 to start with, t is equal to 0 if you do not have any n 2. So, this n 2 will depend on the decay of n 1 and its further decay of n 1 that produces n 2 and further decay of n 2 to n 3. So, this is the balance of these two. So, this is the equation, right. We will now try to find out when this n 2 reaches its maximum point, what is the time when n 2 is maximum. If you want to find that, so when t is equal to t max, means that is the time when n 2 is maximum. If you want to find that, you have to see that the first differentiation of n 2 with respect to time should be 0. So, if I see that, so if I differentiate this equation 2, let us say, so the differentiation will be lambda 1 lambda 2 minus lambda 1 n 1 0, there will be a lambda 1 square coming up e to the power minus lambda t minus, there is a minus, but again there will be a minus coming here. So, this can be plus lambda 1 lambda 2 minus lambda 1 n 1 0 e to the power minus lambda 2 t, that should be 0. If you arrange it a bit, n 1 0 n 1 0 cancels out. So, basically lambda 1 square lambda 2 minus lambda 1 e to the power minus lambda t will be equal to lambda 1 lambda 2 minus lambda 2. So, basically instead of t we can directly write that these are T max and n1 we have removed. So, this is lambda 2 T max. Okay. So, now lambda 2 minus lambda 1 is also common, we can take out lambda 1 will cancel. So, the remaining term is, so lambda 1 e to the power minus lambda 1 T max is equal to lambda 2 e to the power minus lambda 2 T max. That means, e to the power minus, if we make a T max common, then lambda 2 minus lambda 1 will be equal to lambda 2 minus lambda 1. So, I have just divided this one, brought this one to this side. So, this becomes T max. If I take log of both sides, this will be T max will be equal to 1 by lambda 2 minus lambda 1 into log of lambda 2 by lambda 1. This is the expression that gives the T max or the time when N2 will be maximum. Now, if we will try to plot how the number of atoms vary with time, you will see that N1 which is only, so what we are discussing is basically N1 decays to N2, that decays to N3, this is radioactive, this is radioactive and this is stable. In that scenario, if you see N1 which is only radioactive, so there is a constant loss of N1, so you will lose it, and because the loss is through radioactive decay, so they will follow an exponential trend. So, this is your N1. Now, N3 is stable, so it is only receiving atoms and that production of atoms through radioactive. So, again that will also follow an exponential pattern. So, this will be N3. In case of N2, initially because it starts from 0, let us say, and it will gain initially and it will reach a maximum, it cannot go beyond N1. So, it will gain and then subsequently it will also start decaying. So, this is N2 and this is the time when the T max will happen, and the expression for T max is given here, right. This is the expression we got for N2 at any given point of time, where we have been discussing that N1 decays to N2, decays to N3 in a decay constant of lambda 1 and lambda 2. Let us say we will think of a situation something very similar to the uranium 234, where the half life of the parent nuclide is higher. That means, the lambda 1 is small compared to lambda 2, because if T half is higher, your lambda for that particular nuclide has to be low. In that case, you can approximate the e to the power minus lambda 2 T to more or less to be equal, because lambda 2 is larger. And if you want to put in this equation, which was our equation 2 I guess. So, N2 will be lambda 1 minus lambda 2 minus lambda 1 N1 0 e to the power minus lambda 1 T, and your lambda 2 T terms is approximated to 0. So, this will be 0. So, you will end up N2 is equal to lambda 1 divided by lambda 2 minus lambda 1 N1 0 e to the power minus lambda 2. Now, this is the expression for N1. So, we can write N2 at any point of time will be lambda 1 lambda 2 minus lambda 1 divided by N0. This expression holds good only if your decay constant for parent is lower. That means the parent half life is much higher. In that case, you can also approximate that lambda 2 minus lambda 1, because lambda is very high. Lambda 2 being very higher than lambda 1, you can approximate lambda 2 minus lambda 2 to be equal to lambda 2. So, if this you use here, n2 becomes lambda 1 n1 divided by lambda 2, n2 lambda 2 is equal to n1 lambda 1. You remember n lambda, which is the activity, which is the disintegration per minute for an atom for daughter nuclide and for parent nuclide are same at a given point of time, and this is a very peculiar equilibrium situation which is called secular equilibrium, where both the activity of your parent nuclide and the daughter nuclide are same, and this is a very huge implication when we discuss about the dating scheme involving some of the short radionuclide or chain of radioactive decay schemes like 230 thorium or 210 lead. These kind of dating scheme are heavily reliable in the secular equilibrium or its disequilibrium, and that is what we will discuss when we try to understand the application of 230 thorium and 210 lead for chronology or calculating the sedimentation rates. We will discuss that in detail, but you please remember that the activity of a parent and daughter radionuclides, when they are same, that is called secular equilibrium. If you try to put this term in a graphical presentation, so if you take time and in log n value, you will see that n1 will follow a straight line because it is a log term and n1 decay is exponential. So, over period of time it will follow a linear, but with a slope of negative because it is decreasing. In case of n2, we saw that n2 will reach a maximum and then it will continue decaying. So, in this zone the activity for n1 and n2 will be same, and that is what is secular equilibrium. It has a huge application when it comes to 230 thorium, 210 lead or this decay chains and its application for sedimentation rate and flux calculation. We will discuss that later. Thank you.